Welcome to this presentation. My name is Derda. Today I'll speak about architecting for failure. So what is fault tolerance, how to handle failures, and what is a failure actually. So let's start with a simple example. We have some three-component tree service. Our input is like carbon dioxide or whatever. We have the business logic, the photosynthesis process, and the output is the oxygen. So it looks simple. The client-server scenario, like 3 elements, how hard can it be? But what we don't see in this picture is all the different parts that are in place and are also relevant. So if we go from this client network and server into the details, then we have, on the server side, we have like power source, and this includes both power plants, the cables that provide us the power, our local like power cabling inside the data center, our power adapter, the operating system that our servers run on, the load balancers that provide us with the load balancing and that allow us to scale. On the network, we have the network itself, so the cabling, the hardware, the protocol stack, the ISP that provides us with a connection to the internet or multiple ISPs. On the client side, we have the client library, so something usually we provide in form of, I don't know, a binary file or a contract. We also have the software developed by somebody else, the software that can be developed in very strange ways and can include very strange methods of handling our protocol. And also the human factor, which we shouldn't omit here, because usually a lot of problems starts with, OK, it will work. So what exactly is a fault? Does somebody have an idea of a definition of a fault?
Something unexpected.
OK, like what? OK, so let's start from the other side. What a fault is not. So usually when we think about faults, it's about our side of this entire system. So when we say to somebody, OK, so we had a failure, we think that our component went down. And it's not really a failure. It's a problem. It's a problem that we have to address that can cause failure in the future, but it's not a failure itself. The problem on our side could be anything. Technical failure like software bug, power outage, corrupted data, some security attack. The real failure is when we don't deliver value to the customer. When we don't deliver value, we lose the trust of the customer, so they won't come back to us. We lose the money, so they won't pay us for the services we provide. So we won't be able to develop them further. So finally, we lose the entire business, so to say. So there is a way of delivering value without working a system. For example, let's take last election in Poland. The system was, so to say, crappy. It technically worked, technically it was tested, but when the data came in, it just failed. But the elections were held. The votes were counted. OK, there were delays. There were some media affairs about it. But technically, all the procedures went wrong. The business was served. So we delivered the value. The same thing goes, for example, with the restaurant that just opened. It's just the same scenario. They don't have a concession for alcohol, so they allow you to bring your own alcohol. So they still provide a value, a nice time, a relaxed time with your friends. But they just don't operate normally. The examples are pretty much everywhere. Take, for example, healthcare. What happens if the system that operates the hospital fails? Does everything stop? I mean, sorry, you can't die now because our system is not working. Not really. So when we know what a failure is, we can move into fault tolerance. So what fault tolerance is not? It's not making sure your system never goes down. Because it will. It always will. eventually, it will just break because of some bug, some security problem, some client, some operating system update, some so-called oops incidents when somebody just turns off everything and says oops. We also can underestimate the capacity. So you run a promotion, you run a retail website, you have like 10 servers, and the promotion is like going viral. So you have 10 billion customers. Okay, 10 million customers, perhaps. So your infrastructure can't handle that amount of customers. So even if it's the best software ever, without the bugs, with all the redundancy in place, it will just fail. So what is a fault tolerance? It's making sure that system can quickly recover and client is not impacted. So it's all about the client side, not our server side. OK, so how to solve it? Again, do you have any ideas, any suggestions on how to solve?
Redundancy.
OK, all right. Anything else? OK, so the first thing is redundancy, just as you said. And there are a few aspects of redundancy that we should discuss. The first one is hot or warm replicas. The concept is simple. We have like n servers. We keep like few of them just running, but not really in the infrastructure. And in case anything goes wrong with one of the servers, we just replace them. The concept is simple. It usually works. It can help us when there are, I don't know, some short-term bars or some unexpected problems with the hardware. The second aspect is hardware redundancy. So we just replicate our application across multiple servers. We use like 2 power sources, disks that are configured as a write system, network adapters that are duplicated, and so on. The first aspect is the geographical distribution. So take, for example, some like faraway continent, like some island or something that is pretty much remote. When you want to provide services there, you have 2 choices. You can run them locally, so you can put the server there, or you can run it centrally. Of course, the second option is easier. But what happens if the connection between this particular area and your network goes down? You can't serve the customers. So if you want to serve them even if the connection between different areas are broken, it's just as easy as it goes. So you have to distribute in a geographical way. A similar concept to this one is the content delivery network. So pretty much every cloud provider have some offer about content delivery. So basically all the static content you have to serve to the customers, you just send them and they handle it pretty much. The third thing is availability zones, which is usually within one data centers. You have like several physical rooms or something. So in case of a fire or flood or any other such events, you can just switch to another one. Next thing is cache. We usually don't think of cache as a redundancy, but it actually is. So we just duplicate the data. We store it in some way that has shorter access time that allows us to send the data sooner, to not recompile them. In case of cache, we can store a static content, so like CDNs. We can pre-calculate some, I don't know, reports, some queries, some results that would take longer normally. And we can also do it on client side. With HTML5, we can store pretty much any kind of data on the client side. So instead of them hitting our servers with the same request like every minute or so, they can hit their local cache, and we can just refresh them if needed. And the last part is alternative systems and procedures. That's actually interesting because it's pretty much always omitted. So take, for example, some card processing system from a bank. So you had this old mainframe that can run, I don't know, 100 transactions a second, have only a single pipeline because of some blocking issues. So you want it rewritten. So you write a new software, you test it, you deploy it, it runs like a magic, you can scale it. But then something fails. You either discover a bug, there's a security feature, some problem with hardware. If you still keep this old system in place, you can kind of downgrade your service into the old one. So instead of improved capacity and so on, you get the old one, but the server is still running. The service is providing value. The second approach is to solve those issues is with design. The first and I think most obvious one is going stateless. So you can't really scale unless your service is stateless. Of course, you have to store some data in some central database or data store or whatever you use. But the service itself should not be stateful. There are some exceptions, but they have to be really considered for a particular scenario and for each particular case. But the general rule is you go stateless. And the second part is asynchronous and decoupling. In terms of asynchronous, there are some tasks which can run longer than usual, like sending email or connecting to some server to, I don't know, store the file or something. Why don't you return to the client and just let the background job do all the heavy work? This way you can improve the experience of a client, and also we can retry the request if it fails in any way. In terms of decoupling, you usually think of decoupling as separating the system into multiple components. But it's only part of it. What happens if one of the components fail? In most of the systems that I saw and I worked with, the entire infrastructure failed because they were dependent. They didn't handle problems in other components, like with separate layer. So the proper decoupling is about handling exceptions on a component level and not allowing other exceptions from other components to influence your component. The third thing is uniqueness or randomness or whatever you call. I guess pretty much every one of you once upon a time used a timestamp as some kind of request ID or whatever. So it's good as long as you have like less than 1,000 requests per second, where it becomes a problem if you have more. So uniqueness is to provide some really unique value. Not like pseudo-unique, like timestamp, but really unique. You can use random numbers. You can use some information from the network, like IP address plus timestamp or whatever. You can use the hardware random generator or whatever suits your need. The next one is idempotent requests. Do you know what idempotent requests are? OK. Yeah, basically the idea of idempotency is that the request itself, if you retry the request and redo it, it won't change the state of the system. So basically, with the network infrastructure we have, with the protocols we use, it's possible that you receive the same request twice. Let's say the same order. So a client sends an order to your system, and you receive it twice. So idempotent request is making sure that they are not executed twice. So the client does not receive two, I don't know, books, computers, or whatever he ordered. And the ways of doing that is usually by creating an ID of a request based on some customer information, like session key, timestamp value, the hash of his card, or any such information. The next part is sending commands, not data. So for typical enterprise application, which is basically create, read, update, delete, when you send update, you usually send the entire structure. So you want to update an object, you send the entire object with updated fields. This is a problem when there are few components or few subsystems that are working on the same, exactly the same row. Of course, you can use row-level locking, but it will just make your application synchronous, which is probably not something you want to do. The solution is to send commands. So instead of sending the structure, you send a command like change this field to this value. Using this, we can mitigate some of the problems with the data consistency. The next part is auditing, and it's something really important and something we really often forget about. So every change in the system should be logged in some way, either in application log, system log, special audit database, or whatever is the mean. But for every piece of information in your data store, you should be able to tell exactly why it is there and what caused this information to be stored there. It's really a pain to create such application, to maintain it, but if there is a problem, you will regret that you don't have such functionality. The next is enterprise integration patterns. I guess most of you heard about them. It's basically similar to software patterns, but on the system integration level. It gives us maybe not the solutions, but some approaches to some common problems that we can use in our design. They were really created by experienced people over time, and we should not underestimate their value, because usually they describe optimal solutions. And the last part is to break the rules. There are a lot of rules in IT world, like standards, patterns, protocols, like good approaches, and so on. And they are good as long as your application is small, it's like deployed into one server and so on. But if you go into scale, they start to be a problem, to abstract the way you do the business. So to design a good application, you have to know which rules to break. And there is also a procedures part. So yeah, we all know about backups. How many of you create backups like daily, weekly, or whatever?
Everyone.
Okay, that's fantastic. And how many of you test if you can restore those backups?
I just.
Okay, so we have one. Anybody else? Two? Yeah. Basically, having a backup without being able to restore it is pretty much pointless. We have some binary file that we can, I don't know, print like in hex or something, put on a wall or whatever. But if you are not sure you can restore it in like half an hour, then you don't really have to do backups because it just doesn't provide you any value. The second part is continuous integration. It's something hopefully we all do. So it allows us to prevent the most obvious mistakes, most obvious problems with tools for static code analysis or automated metrics. We can really improve the quality of our software. So it can prevent the, so to say, low-level problems to appear. The next thing is the quality assurance and potential problems, which hopefully is gaining traction in Poland in recent years, but it's still not the ideal situation. A lot of companies, so-called software houses, don't have a QA department, or they have like one person that just runs the unit tests. How often have you heard that, okay, it builds, so it works? Because it's a phrase that I unfortunately heard pretty often. And yeah, sure, it's built, so the build process works, but it doesn't mean that the application works, even if the tests are in place. The last part of the procedures is the deployment. So do you know how to do the deployment so that the customer is not impacted? You have like 100 servers, you want to update the software, how to do it? Sorry?
You can use load balancers to switch part of customer request to new version.
Okay. And what happens if there is some contract changes, APIs that are incompatible with each other?
You need to version them, so provide the old version as well as the new version at the same time. So you can
Okay.
accept old requests
All right, so the load balancer decides which version to use?
or the application depends.
Okay. All right, that's the approach that was used for a long time. So we basically take one host out of our fleet. We update the software, we return it to the fleet, and it works. It worked for a lot of time. But the whole idea was created when the hardware was expensive, the network was expensive, so it was pretty much impossible to do it other way. Today, the computing power is like cheap, like very cheap. For the price of having taxi go to the center, you can lease a fleet of 100 servers for a few hours. So why can't you do the deployment to the entire fleet? The way the big companies do it right now is they just create a copy of a fleet. They update the entire fleet and then just flip the load balancer to the new fleet. So this way, the presenters before talked about deployments being done in 3 hours. So for a fleet of few thousand servers, the deployment takes no more than 15 seconds. So 3 hours is not impressive with the computing power we have right now.
But how they verify that this cloud updated infrastructure works, the updated services? How do they verify it?
Okay, basically when you have the entire fleet, you can create some kind of subnet based on this entire fleet. And you can just run a normal test like you would in a production. So you just run entire set of integration tests, which you probably also have to do when you do a one-by-one host deployment, and see if there are any problems. There's also another part to this that we'll talk about in the next slide. And this is observe. So let's start with the second point, observe key metrics. Metrics is pretty much any piece of information that tells you how your software behaves. It might be anything. It might be the average time it takes to complete a request. It might be a number of requests per second, a number of errors that your software generates in particular piece of time. But what you have to do is to observe. So if you do a deployment to a new fleet, and one of the key metrics just rises or goes down a significant amount, then there is something wrong. And what is wrong is the first point, so dive deep and do a post-mortems. We already established that our software is going to fail. So what happens if it fails? The first thing we should do is to dive really deep, so to understand the real cause of the problem. It's not enough to say that, okay, so we got this error on, I don't know, some third-party tool that we are using that's just random error. We don't care about it. What really caused the problem? Was it like misshaped request? Was it some problem with the infrastructure? Was it some problem with security, perhaps? Without doing a proper analysis, you can't prevent those problems in the future. And if you can't prevent those problems, then everything around problem solving just doesn't make sense. The first thing is identify bottlenecks. And actually, we have two parts here. The first one is the, let's say, design bottlenecks. So if we design a system, we can see that part of it will have to handle a heavy load. So it's a potential bottleneck. But what happens is you deploy the entire system. You set up the monitoring around this particular piece, this component, and then something else fails. Because how a system behaves is never how a system was designed. So you have to identify it twice. The first one during the design phase, and the second one after deployment, after implementation, to see how the real software works in the real conditions. It's pretty much the same with the next point, so verify assumptions. To build a system, you have to assume something. You have to assume that you will have 1,000 clients, that your infrastructure will run on virtualized servers, that your network will have this and this throughput, that your database will do something or do not something. So every time you do a deployment, you have to verify those assumptions. Because what happens if you have 10 customers instead of 1,000? And what happens if you had 10,000 instead of 1,000? Those are the assumptions that you have to verify and be able to react really quickly. The next part is predicting traffic. Because the worst that can happen is that your service, your business goes viral, everybody wants to use it, and then your servers can handle it. It's pretty much the worst nightmare that you can have. So I know there are some solutions like auto-scaling with virtualized servers and cloud solutions, but it takes time. On average, it takes about 15 to 20 minutes to just spin on the server, install the application, install the image, and just put it into load balancing. So if you hit a traffic spike that you can't handle, it's already too late. What you have to do is you have to predict the traffic patterns. There are, of course, some standard traffic patterns, like we have a spike in the morning where everybody comes to work and just looking for something to do until they start working. Then we have the spike in the afternoon when everybody gets back to home and, well, just browse the internet. But your service might be different. Your service might hit a traffic spike at, I don't know, at lunchtime because you provide some food services. So first, understand how your traffic will look like, and then predict and react before. Okay, the next part is about trade-offs. Because design is nothing more than just deciding on the trade-offs. I think you all saw this kind of diagram. So can anybody describe what it is? So the idea is that you have to choose two of the three elements that are around this triangle. So you can have a cheap system delivered on time, but with limited scope. You can have the full scope delivered in time, but it will cost you a lot. And you can have cheap system with a full scope, but it will take a lot of time to develop. But is it really true? Because for me, it looks too simple. In real, it's something like this. And it's not even a geometrical feature, it's more like a graph. And it's only a part of it. You have like thousands of factors that you have to take into consideration. So you want your data to be durable? Okay, sure, but what about consistency? What about the cost? What about the complexity? You want your customers to trust you? Okay, sure, but what about the time, for example, or the performance, or the manageability? The real problem with system design is to understand your business, to see what you can sacrifice to provide a better value. So if you are running a bank, you probably want to have high-level security. You want your clients to trust you. You want your platform to be stable, but you can put more money into the system. You can design it and develop it like longer. You allow to have higher complexity. You don't really care about the performance. On the other hand, if you are doing some kind of startup thing, you probably want to cut cost. You want to cut time. Reliability is something not really important. Security, all right, maybe later. Scalability, sure. That's the decision that you have to deal with every day. So to give you an example, there's a service called Foursquare. Did you heard about it? No, not really. Okay, it's basically some application that allows you to tell other people that, hey, I was here, and like share it socially and so on. So it was also a startup at some point. It grew in size. It's really popular, I think, in the States, not really in Europe. But they have a functionality that tells you where to go next. So based on where you've already been, where your friends been, where other people with similar interests have been, it suggests you the place that you can go. Because of the amount of data they were storing, they decided to use the memory. So basically, they have the MongoDB instances that are running on the memory. Of course, the data is stored like on a disk or as a backup, but the whole calculations are done in memory. So what do you think? How much memory their server have, like a year ago? Okay, so it was 66 gigs, with each record taking about 40 bytes. So it was large, and they actually ran out of memory. So the problem was that because they are using the Amazon AWS infrastructure, Amazon wasn't able to provide them more memory within one server. So they decided to shard. They shard the database into 200 shards, divided it into 2 clusters, and then the entire system failed. It failed because of the thing that we discussed before about the keys. Usually, when you have a running system, the newer records are accessed more often. And because they had keys like number, so the latest values were accessed more often than the previous ones. So the latest shards were much more under pressure than the previous ones. So the server just couldn't handle it. The thing is also that they, of course, could have used the database, normalize the data, scale the database, create a cluster, create read replicas. This is pretty much what books teach us to do. But they didn't. They wanted to provide real-time experience for customers. They decided it would be better if they used the RAM memory. So they just used it. They broke the rules. For now, I think they have a cluster of 6 machines, as long as I checked last time, each of 66 gigs of memory, and it's still growing. So that's their trade-off. OK, so summing it up, because we still have some time, but maybe we will have some questions. The first lesson to learn here is learn to live with crashes. Because your system will crash. Sooner or later, during the day, during night, but it will. What you can do before is to learn how to deal with those crashes, to analyze what's the impact of those crashes, and to prepare how to handle them. The second lesson is to automate the procedures. Because you can create a system with, I don't know, manual deployment or manual backup restore or whatever. But when there is a problem, you simply won't have time for such things. You will have a lot of customers calling you. You will have your manager that will scream at you that, why don't you fix this immediately? Having procedures allows you not only to handle the problems more easily and faster, it also allows you to just prevent errors that were caused by human factor. So if you deploy this manually, you can forget about, I don't know, some config or some switch or whatever, and then everything goes even more bad than it was. The third lesson is don't be afraid to cross the line. So crossing the line is something you shouldn't do in a project for university, something you shouldn't do in a project you deploy to your own computer only to automate some task. But if you are going public, if you are going to global scale, you just can't do it within the boundaries of like what is considered normal and standard. So to sum up, the fault tolerance is not a property of a design. It's something that you need to understand, that you just can't design a system that is fault-proof. Because everything changes, your customer changes, the infrastructure changes, your environment changes, the business changes. It's a process. It's a continuous process of fixing your software, of analyzing what went wrong, of just understanding your business, your customers, and your system. So it's not something we can do once and forget, which is unfortunately the approach that is very common. So that's pretty much all. Thank you for attention, and do you have any questions?